All right, let's start. I got your attention. Okay. It's a pleasure to introduce Evgenya Shkolnik for today's colloquium entitled "The Future of Exoplanet Science Missions." Evgenya received her PhD on chromospheric activity induced by short-period planets at the University of British Columbia, working with Gordon Walker. She held postdocs at the IFA and at the Carnegie DTM. And following her postdoc, she was an astronomer at Lowell Observatory before joining the faculty at ASU in 2015. She's also the associate director of ASU's Interplanetary Initiative, whose broad mission is to advance space activities and I think advance the interests of humankind, it says as well.
That's the goal.
Evgenya has been an SSP associate at the CFA since 2021. Her research focuses on exoplanets and their interactions with their host stars. She's active in the development of new space missions, hence the colloquium title. She's PI of the CubeSat, the Star Planet Activity Research CubeSat. I now learned the acronym, SPARCS. And SPARCS will assess the habitability of the environment of M and K stars by monitoring flares and sunspot activity in the far and near UV. And excitingly, SPARCS passed its pre-ship review 2 days ago.
Last week.
So, with no further ado.
Oh. Thank you. All right. Uh-oh. There's a feedback here.
You can turn off the mic so that Dan has put on.
Oh, is that
Oh.
the mic
It's on.
Yeah, I thought I turned it off.
Thank
Oh,
you.
it is on. Okay.
Is my mic on now? No, there's still feedback. My audio's, hold on. Sorry, guys. No. But over here, I'm hearing, oh, I'm going to. Oh, of course, I've got Zoom going. Thank you. So I'm in charge of Zoom. Hi, folks on Zoom. Okay. All right. Thank you, Dan, for that introduction. Thank you for the colloquium committee for inviting me and to all of you for coming today. I hope this particular slide, hold on a second. What is happening? What is happening? Zoom is not letting me flip?
Yeah.
Seriously? Come on, Zoom. All right.
Try to click on the slide.
Okay, let's try this. Thank you. You've done this before. Okay. So the previous slide was here to inspire you and to believe that we are really in a scientific, incredible time. Okay, we as a community are right now designing a space mission to look for life outside of our solar system for the first time. I don't know about you guys, but this drives me every day at work. So typically, and of course I'm talking about the Habitable Worlds Observatory, HWO for short. Now typically these giant flagship missions get all the limelight, which understandably so. It makes sense because they are giant in cost, really typically over $10 billion. And also they have revolutionary capabilities that no other mission can do. But in this talk, I'm going to focus actually on the smaller missions that will be supporting the Habitable Worlds Observatory in the future. I will talk a little bit about HWO, just introduce it, but most of my talk will be highlighting, as examples, 3 space missions that I'm involved in. SPARCS, which Dan had mentioned already. This is a CubeSat that is not much bigger than the size of a cereal box. Now, a family-sized cereal box, though, so that buys you a little extra real estate, and you can appreciate it. And then EVE, which is a mission concept that's going to be submitted to the next SMEX round, and UV Scope, which is a mid-X mission concept that we submitted in 2021, and we'll probably be resubmitting again, and I'll tell you about all these things. So even though, and in general, I wanted to talk about programmatics also, and about how these small missions can help the bigger missions, specifically talking about exoplanets in this talk, but I suspect that my programmatic commentary could be applicable to other aspects of astrophysics, including planetary science and also perhaps even heliophysics, but I would love to hear your opinions at the end of this talk. All right. So over the last decade, we have come to appreciate the fact that entire exoplanetary systems, not just an individual planet, shapes the conditions for planet formation, evolution, and habitability. Right? So it's the disk in which the planets form, it's the sibling planets which form with the disk, within the disk as well with the planet we're interested in, and of course the central star that controls the evolution of the planetary atmosphere. Now, the big questions, no, I don't want to turn up the volume. Anyway, sorry if that's bothering you. I'm not sure how to put it away. Ah, here we go. There we go. And we're back. Back to clicking. Okay. So that's kind of in the last decade, we've really come to appreciate the need for the context of any planet that we study. The Astro 2020 Decadal Survey valued that so much that one of its top 3 themes, as they call them, is worlds and suns in context, right? And that what they're doing is now, given a whole round of community inputs, have managed to boil things down to 4 questions for exoplanet study in the next decade or 2. I'm going to run them by you, so pardon me if you've seen them before, but I think it's important to keep these in mind because this is what's really going to be driving science in exoplanets and their host stars for the next really decade or 2. So, number 1, what is the range of planetary system architectures? What are the properties of individual planets and what processes lead to planetary diversity? How do habitable environments arise and evolve within the context of their planetary systems? And lastly, not just the habitable environments, but looking for the signs of life. How can signs of life be identified and interpreted within the context of their planetary systems? So these are really big questions. No one observatory on the ground or in space is going to be able to answer all of these questions. And we're really going to need a suite of them. Now, of course, the Decadal Survey had lots of recommendations for ground-based astronomy as well. Today, I'm focusing on the space-based ones. So here is the current suite of exoplanet-driven missions. All right, I'm plotting them. It's hard to get them all in the same plot, but depending on what you want to look at. So I chose to look at equivalent telescope mirror size and estimated cost. These are costs not including launch, because the launch costs vary widely between these. They're all scaled to FY $25. And what you see is it starts here, kind of at SPARCS, the smallest of them all, which you'll hear more about, all the way leading up to Roman, the Roman mission here. So the way I'm going to talk about these is in terms of small missions, so about $100 million or less, medium-sized missions, about $1 billion or less, and then the flagships up here. So even though Spitzer and Hubble and JWST, of course, have done wonderful things for exoplanet science, they were not originally designed to do exoplanet science. It was not a driving science case. And what I mean by that is a science experiment that helps us identify the instrument capabilities that we need and the mission architecture. It doesn't mean that these missions are only doing that one or 2 exoplanet science cases. A lot of these missions do a ton of other science, but they did have originally a science driver based on exoplanet science, okay? And Roman is actually our first flagship mission that has an exoplanet science driver, and that is the microlensing survey that Jennifer Yee talked about very nicely a couple of weeks ago. So here is a representation of the current opportunities to apply for time in order to lead a space mission if you're interested in any scientific endeavor that you need a space telescope for. So these are scaled in diameter by cost, okay? We have the medium explorers, also called the mid-X's, with a $300 million cost cap. Again, that is without launch costs. This is what we call the PI mission managed cost cap. So this is the money that the PI manages themselves and with their team. The small explorers, also called SMEX, at $170 million. Of course, there are 2 mission of opportunities you might have heard of that also come tagged along with some of these announcements of opportunities. And the latest are the smallest ones, the Pioneers and the CubeSats, are relatively new, not that many out there. No pioneers are flying yet, and only 2 of the CubeSats are right now flying that have been funded so far. And for those of you who love probes, let me explain quickly why I excluded probes from here. Probes are this $1 billion PI managed cost cap, and I excluded them because, according to the AO, about 75% of their time is going to be guest observer programs. So in my mind, they're really like mini flagships where lots of people can do lots of science, different kinds of science, as opposed to the explorers that tend to be more focused. Okay? So the 3 that I'm going to talk about, there's 3 missions and 1 goal kind of in my brain. As Dan mentioned to you, even since my PhD work, so for over 20 years now, I've been thinking about the planets in context and the interactions between planets and stars specifically. So I'm going to talk about SPARCS, that looks at the stellar radiation and flare environment, EVE, about planet formation and early evolution, and UV scope, atmospheric structure and loss of exoplanets. And all of them have this important point of being planets with atmospheres that orbit stars. Okay, and thinking about that in the broader context. So I'm going to give you a few minutes of background about why understanding the energy environment due to the star onto the planetary atmosphere is important, and specifically at the high energies, because that's where a lot of the photochemistry and photoevaporation is dependent on. So first of all, we typically split up our planetary atmospheres into 3 sections. We've got the exosphere, and studying the exosphere can help us answer some of these questions. How much mass is being lost to space across the diverse planet population, and what is sculpting the radius distribution of known small planets? We also talk about the upper atmosphere, where, like, what is the composition, right? Are there clouds? Are there hazes? What is the mixing, the distribution amongst the different layers? We think about that in terms of the upper atmosphere. And then there's the lower atmosphere, of course, which is very nicely probed by optical and infrared, and JWST is doing a wonderful job of looking at lower atmospheres of exoplanets. But the high energy environment of all these levels truly impacts our observations even at other wavelengths. So I and many people, it's become a pretty important question that lots of people have dove into, is what is the radiation environment? We have the extreme, the X-ray and the EUV photons really being absorbed up in the exosphere. And they run from about 10 to 100 nanometers. The far UV can probe further down, and they impact the photochemistry along with the near UV lower down. So we have mostly photoevaporation caused by the extreme UV and X-ray, which we collectively call the XUV, and then photochemistry down below. So we've spent lots of time in my group and others trying to understand and characterize the UV evolution of stars as a time since planet formation through the evolution into old ages now, where we can try and interpret the planetary atmospheres that we are actually able to detect and those that we are not able to detect because they might be gone completely. So this is a summary plot of many papers from the HAZMAT program, which stands for the Habitable Zones and M-dwarf Activity Across Time. And here's what I'm plotting here for you. UV flux, in particular right now, I'm looking at the far ultraviolet incident on a planetary atmosphere in the habitable zone of these different stars. So if you look at the late M's, it's red here. And you see how it evolves over time from early ages to late ages. M and K, early M's and K's tend to follow pretty similar path in evolution. And the sun-like stars is actually a bit of a mystery. It's really remarkable how little we know about the UV evolution of the sun across its age. I mean, there's some X-ray programs, but the UV has not been excellently probed yet. And so Tyler Ritchie-Yowell, my former graduate student, is looking at the HAZGAT program, as we call it now, habitable zones and G-star activity across time, because we still really need to understand that for a whole host of reasons, including the Habitable Worlds Observatory targets. One thing I wanted to point is, why are these lines so fat? right? They run almost an order of magnitude in width. And the reason isn't a measurement error. It's the intrinsic variability across a sample of stars of the same mass and age. It means that if you look at one, say, late M at 100 million years old, it will not necessarily have the same baseline or quiescent emission as another equivalent M star. And there's a whole host of reasons for that. But I think that's kind of it was an interesting and exciting measurement to make. Okay, so what we did was we looked at this quiescent evolution, and we applied these to some planetary atmosphere models. Here is an example of an Earth-like planet orbiting an M star, and what would its reflectance spectrum be? So something that HWO Worlds Observatory is hoping to do is to look at the reflected light off a terrestrial planet in the habitable zone of its star. So in this case, what you see, all these differences here is not because the planet atmosphere is different fundamentally. It has the same composition for each of these simulations, but the ages of the stars, the evolution of the quiescent UV emission is changing with time, and it drastically changes one of our favorite biosignatures, the ozone in the UV, but also lots of these other molecules we're going to be interested in. So this is one point to make. But as you all know, quiescent emission isn't the only thing that's happening in these stars. They also flare. So you have that nice baseline, that continuous nice baseline, but that's not so stable. And especially in M stars, we now know that they are very energetic and active in the UV particularly. I mean, they are, but in optical as well, and as we've seen in some JWST spectra, even in the infrared. So here's just an example of a Galax flare that was caught on an M4 star. This is a mid-M that increased by 10 UV magnitudes in one flare. Okay? I mean, that's incredible, and quite, I think, a surprise for a lot of people. Here's something from the HAZMAT program. This is HST spectroscopy. This is a light curve of HST spectroscopy, far UV spectroscopy, called what we call the HAZ flare, because it came from the HAZMAT program. But it is a very strong flare. It grew by a factor of about 175 in 200 seconds. This holds the record for the strongest M-dwarf flare observed with HST, so much so that they cut us off from doing active M stars, because they're afraid that we're going to damage the UV detectors. So we actually have no mechanism right now by which to study the far UV of active nearby M stars. Yeah, it was a fight, and I lost. Okay, so another example of a rather spectacular flare, although intrinsically less energetic, is on our favorite Proxima Centauri, our nearest stellar neighbor, which also hosts our nearest exoplanet. This was a program led by Meredith McGregor, where we observed simultaneously TESS, HST, and ALMA data of Proxima Centauri for 36 hours. And we caught a couple flares. Here's the strongest one, where we were able to catch multiple wavelengths. And what you see here is in the far UV continuum, you see an increase of 14,000 over 5 seconds, where the exact same flare in TESS data, so in the optical, was a factor of 10. Okay, so what's that telling you, right? That's telling you that the predictive power of an optical flare is weak, to say the least, in the ultraviolet, right? Right now, we have about 30 flares total that have been observed simultaneously with TESS and with SWIFT, which is can observe in the near UV. So there's just not that many. And one of the goals, I'll talk about it, one of the goals for EVE is to do multi-band flare photometry in order to characterize these flares and really understand what their temperatures are. Are they a single black body? Are they a two black body component? Like, we just don't know, which is remarkable. Here's the HAZ flare again, showing you how we were able to fit. So here it is during quiescence. Here it is during the flare. This is now like the spectroscopy version of the light curve I showed you before. And we were able to fit a 15,000 degree black body to this curve, which is very different than the canonical 9,000 Kelvin, which is what people typically apply as flare temperatures. So again, we've got lots to learn, that's for sure. And here's just another nice example of if you want to look at the spectrum of an M star during two different flares, one at 9,000 Kelvin and one at 14,000 Kelvin, you can see that in the optical, they generally don't change that much, but in the parts of the wavelength range, in the far UV and the near UV, where we expect, where we know is the photochemical impacts are greatest, it's a huge difference. It's just a huge difference. So what have we been able to do thus far through both the HazMat and the MUSCLES program is to look at the evolution of the flares. So I showed you before the evolution of the quiescence. Remember, it was kind of went high and then low. And now I'm showing you the evolution of the flares. And you can see that young M stars flare much more rigorously than old M stars, and we don't really know much about the young sun-like stars. Okay. So what we do now that we have these flares, so now we have a combination. We have the evolution of the quiescence, we have the evolution of the flares. We combine them here in this plot, and we can then apply this kind of X-ray luminosity to planets. So this is just one example, because I would say that it's been slow going to get the data that you need in order to do this and to find people who are interested in modeling this in the first place. And so what you're seeing here in AUMIC is that, this is for one of the planets of AUMIC, the Earth-size one, is that it should not have an atmosphere. The atmosphere essentially should be completely blown off, but if you take the same planet and move it out to outside beyond the habitable zone, it should have its atmosphere still. So distance matters, the evolution of the flares and the quiescent matter, and of course it just depends on what you're looking for. All right. Similarly, these are just examples, but so this is just another example here with JWST data. If you impact it with flares of different temperatures, you get different photochemical impacts on the SO2. Here for the reflectance spectrum, also you get a very different response of if you have a simulated HWO reflectance spectrum, whether or not you understand what is happening in the planetary atmosphere. But I will say, the unexplored parameter space is vast. Like we don't know we don't know what the impact will be on all sorts of planets yet. We don't know what the flares will be like on a range of both planetary distances, but also the stellar components. Okay, so to get into how we're trying to solve some of this is with these three missions: SPARCS, which is supposed to be launching in 2025, EVE, which, as I said, is a mission concept yet to be submitted in 2031 if it wins this round, and UV Scope potentially in 2033 if all goes as planned. Okay, SPARCS, the Star Planet Activity Research CubeSat. Those of you who come to 10 a.m. coffee have seen me with my mug and probably have heard me talk way too much about it, but I've been very excited about it. This is the mission I've been leading for a few years now. It has three general goals: science, technology, and training. The idea is that we can observe simultaneously in the far UV and the near UV, photometrically, of 20 young and old low-mass stars. So we want to look at the flare energy distribution, but really stare at it for a month or so at a time per target, right? Like I said, HST observed Proxima Centauri for 36 hours, and that holds the record for the longest that HST has observed any M star in the UV. So we want to do months at a time. We also are flying new technologies, two new UV technologies, which I'll mention in a minute. And these are important because it means that once we have developed them in the lab, tested them in the lab, they can be used for bigger missions. And then once flown, they can be used for things like Habitable Worlds Observatory. And then, of course, we train. This is what Smallsats are so beautiful for, is training students and new mission leaders of all ages. This is the SPARCS team. The people in green are the junior people who really have done a tremendous job here, including a bunch of undergraduates here who were in the lab 24/7 during testing. When you have things and you need to cycle the students through it, these spacecraft tests sometimes need a week long of 24/7 testing, and these young people have absolutely saved us. We have a couple of PhD students who have already graduated and moved on to bigger missions. And even the senior people on this group, remember, CubeSats just started a few years ago, so no one on this team had ever built an astronomy CubeSat, or any CubeSat for that matter. Like this was brand new for astrophysics, and so we all did a lot of learning, and many of us here on this list are also working on bigger things as well. The technology mission here is to fly these high quantum efficiency UV detectors developed at JPL, where you can see we are doing much better than GALEX, the old detectors last flown on a NASA mission. And so now all the testing of this and also the integrated filters that we're using are part of the UVEX mission. Some of you might know this was the selected MidX mission last round, and they're flying our technology because we were able to test it all in the lab. They can do it. Our optical design is pretty straightforward. We have a tiny 9-centimeter telescope, not 90, just 9. I want to make sure you heard me. And with a dichroic, and it just breaks the light up into the far UV and the near UV. And like I said, we're going to look at flares. I just want to make sure that I have time, lots of good time for discussion. And so you saw this plot before, right? Here we have the flare frequency distributions, the ones that we were able to do up until this point based on HST data, anchored by the strongest flare that has flare. But we want to extend down to these rarer, stronger flares. So we need to understand what happens to this curve. Where does it turn off? How far do these flares actually go? How strong is a once-a-month flare on an M-star? So, of course, I'm obligated to show these. Actually, I had many more of these, and then I thought it was kind of getting a bit excessive, like showing baby pictures, because it's so exciting. And for any of you who have delivered any kind of instrument on the ground or in space, this is enormously exciting. But my husband assured me 2 was more than enough. So this is SPARCS right there. You could fit it in your backpack. This is the dispenser we had to do that day, a fit check. This is me pretending like I'm useful in a lab. And this is Nathaniel Struble, our mechanical engineer. You can see here we have the solar panels folded in, and here we're testing them, their deployability. It's very exciting. I mean, I really could go on, but for the sake of time, I shouldn't. But as Dan said, we had our pre-ship review last week. We passed with flying colors. We actually could launch tomorrow if someone would take us. So we are manifested on a launch, not till October of 15, but of this year. So right now we are in a pseudo storage in our lab at ASU. And I say pseudo because there's still work that has to be done. You can't just like store a far UV, a near UV spacecraft alone and unattended. But we are aiming for launch October 15th from Vandenberg. You're all invited. Drinks on me. Okay, so the next one I would talk about is EVE. Now, EVE is not funded yet, as I said, and it has not yet even been submitted. So this is all very new and exciting kind of work. This mission is led by Meredith McGregor, whom I expect you all know. I am the deputy PI here, and we have a wonderful science and technology team. And the main exoplanet science drivers for this mission is to detect young planets, to study the evolution of primordial atmospheres, to also study the flares, as I said, in multicolors, multibands, and study the initial conditions of planet formation, because we'll also be able to probe accretion signatures. I don't have time to talk about all of them, all the science, but just to give you kind of the overall framework, it's going to be 3 telescopes combined into 1 spacecraft, but doing near UV, optical, and near infrared simultaneously. This has never been done in a single spacecraft, and we're very excited about it for a bunch of reasons, because it solves a bunch of problems. Multi-wavelength flares, looking for young stars, right? Looking for young planets around young stars, because young stars are notoriously active, right? It's very hard to find planets around young stars, and if you can get your transits at different wavelengths and mitigate for stellar activity simultaneously, your yields go up dramatically. So Like I said, 3-band photometry. We have fast observing cadence to catch the flares. We're going to do 30-day stares at least 15 pointings. And these pointings are of young clusters and with large field of view, 25 square degree field of view. And here's just an example of some of our planned targets. We have the Orion field here, which is just really young, 1 to 5 million years old, Upper SCO at 5 to 11, and then these here at 10 to 20. And then we have a few even older ones, so we can look at the evolution of that, of the stars and the planetary atmospheres. And just to say a little bit about the science, just one part of the science that I'm particularly excited about with Eve, and that is trying to answer this very fundamental question right now in our field, which is why do small exoplanets come in 2 sizes, right? So the Kepler and TESS missions have shown us that small planets, come with super-Earths and sub-Neptunes, and it's a big conversation in our field as to understand why that is the case. One answer could be the evolution, right? So what we call the gas dwarf hypothesis. So the sub-Neptunes evolve into sub-Neptunes and super-Earths, or formation, something that's called the water world hypothesis, where actually the super-Earths and the sub-Neptunes form in completely different regimes. The important point here is that at the end of all this, so in very old systems, both these theories would form this distribution, right? But that distribution, the radii distribution changes for young systems. So the goal here is to probe these very young systems in order to disentangle the science or the formation mechanisms of these sub-Neptunes and super-Earths. So that's just, like I said, it's just one of them, but it's there's not enough time to cover all the great science that Eve will do, but hopefully once it's submitted and wins, you'll be hearing lots and lots about it from me at coffee with a different mug. So the last one is UV scope, which you've probably heard a bit about from me already in the past and certainly over coffee, because when I first arrived here on my sabbatical, this was the mission I was deeply working on for submission to the MIDEX program. And here now we're taking, rather than doing photometry like SPARCS and Eve is, doing full-blown transmission spectroscopy, but in the ultraviolet, in the near UV and the far UV simultaneously at moderate resolution. And so we can get all the way from Lyman alpha to the optical in one snapshot. That's the goal of the mission. There's lots of other science this kind of capability can do, but it's really driven by transmission spectroscopy at high energies. So looking for what is actually blowing off the planet, both at Lyman alpha and at metals. And also, so here, what am I looking at? So the Lyman alpha tail, you might have seen this already in past talks, that we have already observed, right, hydrogen gas being evaporated off planets. It's already been done with HST. We just now need to do it with a dedicated mission, so we could do this for hundreds of planets, something that is very hard to do with a flagship mission because you're sharing your time with the entire community and all through guest observer programs. So it's just very hard. I mean, I will say that the whole HAZMAT program is probably, I don't know, maybe 250 or more orbits. It was 2 large programs so far. And it's a total of about a week or 2 of HST time. Like imagine if you had a whole dedicated spectrograph to do and all of this. Okay, and we also want to do transmission spectroscopy of the large planets as well. So again, this is very complementary to what is already happening with JWST, what will be happening with Ariel. But really, again, this is where HST turned into a beautiful pathfinder. HST has done this already for a few hot Jupiters, but has only done it for just a few, right? To do population-wide statistics, you really want to do this for hundreds of planets. All right, so although these and other exoplanet missions do important things, none of these will detect life. And I started out with what is really driving me, right? My big overarching question of my entire career is what is the distribution of habitable environments in our galaxy? I say it so fast because I say it all the time, because it really is what drives me. And so I'm very excited about the goals of the Habitable Worlds Observatory, which they dub now a super Hubble to search for life in the universe and do other transformative astrophysics. So this is just one architecture option. It's not necessarily going to look like this. This is just one of probably what will end up being 5 things for us to mull over. And so you'll be seeing different kinds of architectures over the coming years, I'm sure. And like any good flagship mission, the HWO will do all sorts of science, including exoplanet science, but all sorts of science across the solar system, through the galaxy, through the cosmos as a whole, including looking for life down here on exoplanets. And one way the program now, the project office is working in order to collect these science cases that might turn into driving science cases for Hab Worlds is through these community working groups. Has anyone here been part of any of these or contributed to any of the science cases? Well, there's about 70 now running through these 4, and looking for life is just one, but it is certainly going to bubble up to be a driving science case, because this is something that everyone, for the most part, well, I guess not everyone. Lots of people are very excited about this, myself included. And so the idea is for Hab Worlds to be able to image total solar systems, look at habitable Earth-sized planets, potentially habitable Earth-sized planets, and look at the reflectance spectrum. So this is a plot that was taken from the LUVOIR final report back in 2019, but it completely demonstrates what kind of things the Hab Worlds Observatory wants to look at. And this reflectance spectrum of Earth at different ages, so you're seeing here column mass and age, and these kind of spaghetti plots. You can see how the oxygen starts out low, increases, and it gets higher, and therefore with different compositions at different ages, you get different reflectance spectra. But one thing you'll notice here is that the hazes and the oxygen and all these elements that I talked about earlier are impacted by their central star, right? Through photochemistry. The existence of the planet is impacted through photoevaporation, potentially, from a central star. So whatever Hab Worlds Observatory actually observes, it's the context that will help us understand it, right? And this is why I think that the combination of all these other exoplanet-focused missions can do is they can work together in order to help Hab Worlds Observatory succeed. So going back to this telescope size versus cost plot, I've now added EVE to it, UV scope and Hab Worlds Observatory, none of which are fully funded, so they don't get to be white, they're in green. EVE here, I put the +4, is because there are 4 that I know of exoplanet-driven SMEX proposals going in this fall. So EVE is just one of 5. There could be more. And there's no guarantee that EVE or any of these will be picked, right? It could be a non-exoplanet mission. It could be a non-technology demonstration mission for Hab Worlds. There's no control. Really, we have no control right now as to what will be picked here or here in order to support the Habitable Worlds Observatory. So, going back to this, our very nice NASA string of portfolio string, thinking about how these missions can help support Habitable Worlds Observatory, here's Habitable Worlds Observatory scaled by diameter to cost. That's an $11 billion circle compared to the others. Let me zoom out. Okay, so the entire NASA portfolio is just a few percent, 2 to 3% of the total budget of the Hab Worlds Observatory. So my pitch is this. I think we should take 3% of the Hab Worlds budget and devote it to small missions, small and medium-sized missions that will do precursor science, not just in exoplanets and whatever we need, right? And technology development, again, what we need on the time scale in which we need it, and not leave it up to chance. That's what I think. And I think that we really have to invest in these smaller missions. I do feel like they have an outsized impact and would be a great investment for Habitable Worlds. And frankly, I think thinking small lets us think big. Thank you.
Thank you very much for an uplifting orbital talk here. So I'm sure we have some questions. I'll start here and I'll come over to you in a minute.
Thank you. So, I mean, I like your pitch for the small mission as a way to understand what we need to look at with the habitable world. Are people scared that if they put money on small mission, then the big mission is going to change? Or, I mean, there could be an impact because we learn, for example, that within the parameters we can look at, there are no planets with life.
Well, it would be good to know.
Yes, exactly.
But we're not going to be able to solve everything with small missions. Small missions are very dedicated, right? Have very limited capabilities, but can do 1 or 3 experiments really well. But if we're learning from them such that we make the most out of an $11 billion mission, then I think we should absolutely do that. We can't hide from the information.
Okay, so you said something that interested me when you said you wanted to take, and you gave a specific number, 3% of that HabWorld's budget and move it down into the smaller missions. For one, I couldn't agree more, but that says that something's got to go from HabWorlds because it's not, you know, when they come up with the budget, that's what they're planning to build to. So does that mean you think that HabWorlds is overly ambitious? Because you know, the argument here is that it could be 3% smaller without losing anything.
Well, there's such a thing as margin. There's lots of margin. And 3% is a small fraction of the margin. So it's how you want to consider risk reduction. I see this as a risk reduction activity. And as a PI, even though HabWorlds doesn't have a PI per se, but as PIs of smaller missions, it is up to us to distribute margin, right? So one could choose to distribute margin this way as a risk reduction.
Sort of technical question about the spectroscopic UV mission that you mentioned. You're saying you want to probe Lyman alpha. Unless it's somewhere far away from Earth, how do you plan to tackle this problem of the coronal emission in Lyman alpha?
Great question, and that's why we're aiming for L2, for exactly that reason.
I'm wondering if your current project will have enough targets where you can see what the UV flaring is like as a function of mass. Particularly, you're not doing any brown dwarfs, but it might be an interesting thing to get to. So
I think that would be it'd be an exciting science case. I don't think we have the sensitivity to do flaring on brown dwarfs in the UV. I think, I know people have even tried with Hubble at 2.4 meter telescope and have not been able to catch UV flares that I know of, that have been publicized. Maybe there's some. We don't have plans for it. And we are pretty focused on the early M's right now because that's where we're most sensitive to. We could look brighter. So if we finish our primary mission and it's still functioning a year later and we want to go on to year 2 and we get the appropriate funding, then we can move on and do brighter things. But I don't think we're going to get much fainter.
I have a question on the science of the atmosphere loss. So I think the plots you were showing was a hydrogen dominated or hydrogen, pure hydrogen nebula. So if the atmosphere is heavier, how much does that change the picture? And at what point does the hydrogen are you expecting the hydrogen to drag along any sort of heavier molecules and elements? At what point do you get sort of a segregation in what is leaving and what stays behind? And at what point do you expect to stop having any atmosphere loss at all if you have a, I don't know, CO2 dominated atmosphere or something like that?
I think that's a great question because, what it highlights is how limited the current modeling efforts have been. That has not been fully modeled. I can show you, like in this plot, for instance, right? These are the so-called water worlds with the heavier atmosphere. And they're just assuming, a heavy atmosphere of a particular mean molecular weight. And I refer you to James Rogers' excellent paper on the archive right now, where he explicitly, he designed this experiment for Eve. And he discusses the range that he measures, or the ranges of the mean molecular weight that he estimates here, but even then it's very narrow. Like it's just looking at hydrogen, helium dominated water worlds. Like it's 2 points right now. But yes, more.
All right, me next. Okay, so all of the smaller UV missions, if there was no habitable worlds,
Yeah.
okay, they would still be compelling. We'd still do them in
Totally.
and of themselves. And I'm sure that's the case that each of those proposals makes. But here you're introducing this idea that they will help us with habitable worlds. And so I'd like to understand exactly what that relationship is. So are you saying these smaller missions will establish how UV emission varies with stellar mass and age and environment, and then we might change how we pick targets for habitable worlds?
That's one thing.
Or are you saying that these missions will look specifically at the same stars that habitable worlds will look at to tell us their emission now? So I'm just wondering what exactly
Yeah.
is the relationship? If you just could give a few more minutes on that, that'd be great.
For sure. Okay, there's actually a whole bunch of answers to that. So first of all, if these missions all fly before HAB worlds, it tells us perhaps what targets we should be focusing on and which to avoid, because maybe we don't have an expectation of any planetary atmospheres, as one example. Another one could be characterizing the stars you're going to look at longer time scales that you can't do with HAB worlds. So for instance, one could fly a small sat simultaneously with HAB worlds and do the long baseline monitoring, say, in the ultraviolet that you cannot do with a flagship mission, right? So I have often wished I was thinking about this 20 years ago and had proposed that JWST fly with its own UV spacecraft that it can do all the simultaneous observations. That's one way. You could also, other things that we have to do that is not well established yet is contemporaneous versus simultaneous UV observations necessary? Not known, because we need to model it and understand what the impact is at the time of observation. If a star flares dramatically, what is the response on the planet? Is it detectable? Is it fast? What is the time scale? What is the relaxation time of that atmosphere? These are things that are totally open questions. And we have to dig deeper with more missions potentially and figure out if we need simultaneous missions or not. I'm not sure.
Okay, Igor, number 2.
Okay, and a question about flares. I'm wondering if you could actually use existing far UV observations of galaxies to constrain the duty cycle and the power spectrum of these flares, like in terms of power. Because, if you take an elliptical galaxy, it would have 10 to the 12 M dwarfs in it. And if you multiply your, basically the flux from your flares, like, 10 to the 32 arcs per second or whatever, by 10 to the 12, and then think that, okay, if it's 3%, or 5% duty cycle, you can estimate the flux you expect in the far UV. Of course, it will be contaminated by horizontal branch stars and stuff like this, but I think it can be a useful constraint.
This is a question I have for Charlie Conroy, because he's been thinking about, he told me once, I think he even has a paper on Lyman alpha as a measure of M dwarf fluxes in other galaxies. So it's an interesting question. I have to think more deeply about that and if you can really tease out a duty cycle.
2 questions. Would X-ray monitoring continuously be important? It's going well beyond the far UV,
Yeah.
but soft X-rays to hard X-rays. We're studying a mission that we plan to propose as a mid-X that would provide this, as well as all sorts of other science that we want to do. but we thought about exoplanets as something that would be of real interest.
Yeah.
The second question, if I can ask two, is you didn't tell us what are the critical measurements to make in order to detect life. I know that's a very naive-sounding question, but
It's a hot
is there
debate.
In 10 or 20 seconds.
It's a hot debate. It's a hot debate.
Yes.
Okay, let's go to your first question about
Well,
X-ray.
convince us that Hab Worlds could do it.
Oh dear.
No, you don't have to convince us, but you could say, what's being
Okay,
advertised.
let's go back to your first question, though, the X-rays. It depends on the sensitivity. It depends on the predictive power, meaning how well does an X-ray measurement predict the wavelengths that you're most interested in, at least from a planetary atmosphere perspective. Sure, the X-rays could be interesting for flare physics and coronal heating, no doubt about it. But for the planetary atmosphere, we want far UV and near UV, and EUV if you can have it, but the challenge with the EUV, of course, is the ISM absorption. So the vast majority of exoplanet host stars will never be observed in the EUV. So we have ways of trying to predict the EUV from far UV and near UV measurements, which have shown to work better from the UV side than from the X-ray side because of the way the stellar atmosphere produces the far UV and the EUV as compared to the XUV. It has to do with whether the emission is coming from the chromosphere, the transition region, or the corona, right, and where those emission lines are coming from. We've done a lot of work on that predictive exercise, and at the moment, the far UV kind of wins as far as that goes. But if you had a very sensitive, if we did the precursor science one needs to say, okay, if you see a flare in X-ray at this energy with this duration, what is that telling you about the EUV, the far UV, and the near UV, then maybe there's something there to talk about. But I don't think that's currently what is happening. But you'll know more, I'm sure.
So there's two kinds of flares, and you talked about sort of the white light flare that leaks over the FUV.
Yeah.
There's also the X-ray flare that leaks over the other way, that if you have and we have systems here that can measure it, you get the two energies, and we have more than two energies, you can go that other direction. Okay. And who wins is sort of a function of what the type of flare it is. The strong X-ray flares do a lot more EUV than a mild white light flare. So.
Right.
But
we don't know.
Seem to be different physics, and that's sort of that's where we run into who wins.
So to your second question, okay, I don't have a whole talk on biosignatures, but let me just point out something here. Okay. So this is the reflectance spectrum that people have been touting for quite a few years here, and a lot of this, a combination of these are considered biosignatures. Of course, that all really depends on the context, and there's a really excellent paper led by Vicki Meadows, 2018, where she goes through all the false positives and false negatives that we as a community at the time could think of, right, for destroying O2. The same exercise is going to happen for all the other things. We just haven't done it yet. It's something we're going to be working on as a community, not necessarily me personally. I can be a cheerleader on that front. But we're going to have to work out what all that means. There is a science case that I am part of, led by Sarah Walker, also out of ASU, of life as we don't know it, something that tries to get away from the biosignatures. And that's a whole separate other talk as well. But I think people are trying to do their best to figure out what is really a biosignature. And by putting it in the context of the stellar host is key. And then, of course, we have to then talk about the sources, right? We talk about the sources in the sinks. We have to talk about what's outgassing. That's where the geophysicists are coming in. And it becomes a really multi-community, interdisciplinary effort.
Well, a lot of interesting questions, and let's thank our speaker again.